And then you have a matrix such that the ijth entry is xi transpose times xj. So if you like, I can just write that. That is the matrix, which is capital X transpose, where X is this kind of a broad matrix, n by m. The matrix whose rows are my m points. So this matrix actually has pretty low rank because I can express it in this way. Right? The one way to say it is that the image of this matrix has to be pretty small because it's contained in the image of multiplication by X transpose, which is like a highly rectangular matrix, so it can't be very much. Yeah, I'm realizing that I slightly I slightly miss. You should probably think of, okay. We're good. The image of this matrix has dimension at most n. So let me write. Did I say this? So this has rank at most n. So as long as we think of m as being like much bigger than m, which of course it should be, because if you're like much smaller than n, I mean, you could do a one distance set, as we discussed. So you should think of m as pretty big and n is pretty small. So rank n is pretty small because this matrix is m by m. Okay, so conclusion, and because of this formula, I mentioned that the rank of can be expressed as like the minimal number of rank 1 matrices you need to add up to get it. The rank of the sum of two matrices is at most the sum of the ranks. So here you have something rank 1, here you have something of rank at most n. So the rank of this matrix is less than or equal to n plus 1. Should be less than or equal to. Okay, so again, I'll emphasize here, I did not use that A was an S distance set. What I just said would be literally true. I had to take any m points in Rn, and this distance matrix I make has pretty low rank. Okay, now here is a fact. I'm not going to prove this on the board, but I'm going to ask you to believe it, and it is not too hard. If I have a matrix and I make a new matrix I pick a polynomial and then I apply that polynomial to each entry. That's kind of a weird thing to do, right? I mean, we know that that's not, it's something like our students, we say square a matrix and they like square each entry. And you're like, no, that's not what I want you to do. Okay, that's not what we mean by squaring a matrix, but it is something you could do. You could take a matrix and square every entry of it. And a very useful fact is that that has a controllable effect on what the rank is. So again, I'm going to be sloppy about constants, but I'm just going to say if you start with a matrix of rank R and you apply a degree k polynomial to each entry, and by the way, I mean the same polynomial to each entry. So I pick a polynomial and then apply it entry-wise. Then the rank of the resulting matrix is basically also just gets raised to the k power at worst. So for instance, if I take a matrix and I square every entry, its rank is going to at worst square. Okay. So what polynomial am I going to use? Well, it's very carefully chosen. I'm going to take the polynomial x minus alpha squared times x minus beta squared. There's a perfectly good degree 2 polynomial. And if I apply that to the entries, I get a matrix B. And now, finally, I'm going to use the fact that my set had this special 2-distance structure, right? Because go back and look at what this matrix was. All of its entries, except for the diagonal, were either alpha squared or beta squared, which are the roots of this polynomial. So on the one hand, this matrix B, let's sort of ask some questions about it. There's 2 things I know about it. I got it from taking a matrix whose rank is the most n plus 1, namely A, and applying this quadratic polynomial to each of its entries. So I know that the rank is at most n plus 1 squared, or maybe some constant. I'm going to be lazy about that. On the other hand, I kind of know B is. It's this matrix, right? Because all the off-diagonal entries go to 0, and all the diagonal entries go to the same thing, alpha squared, beta squared. And so we know what its rank is. Its rank is m. So it has low rank, but it also has high rank. And that's a contradiction, or at least it's a contradiction unless m is pretty small. So we conclude that m is at most some constant times n squared. And that's exactly the right order of growth. That's what Blockhouse shows, and it's exactly what examples show is the right order of growth. So this rank argument gets you what I think is, at least to me, it's not somehow visible that that would be the order of growth of the answer, but that's exactly what it is. And I would comment that I used 2 here for 2 distances, but I could have really done the exact same thing for s distances and shown that there was a bound of the form n to the s. And indeed, that's what Blockhaus really shows. And that too is essentially sharp. So the right order of growth for how big can an s distance set be in Rn is on order n to the s, which I think is not at all obvious that that's what it would be from sort of purely combinatorial means. And I actually don't really know a sort of, I mean, there are people who know a lot more about extremal combinatorics than me, so maybe it's just my ignorance, but I don't know sort of a non-linear algebra proof of this geometric fact. Okay, I think we are ready to go beyond rank. Let's see what my slide says. Yes, beyond. Okay, so here we go. So now this is great because we used about half of our time, which is exactly what I predicted. And now I want to talk about generalized notions. I want to talk about tensors. So, you know, the most naive notion of what a matrix is, before we sort of become grown-ups and we study abstract vector spaces and we're like, it's a linear transformation, blah, blah, blah. We're just like, it's a rectangular array of numbers, right? In high school, that's what we're told a matrix is, if we're told at all. So we can think of a tensor as just that way, except a higher dimensional box. So let's just start by saying a tensor is an n1 cross dot 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 cross nd array of numbers, where d is what you might call the degree of the tensor. So d equals 2 is a matrix. And what I want to talk about for the rest of this talk is what happens when d is bigger than 2. And actually, just because it's easy to write down, I think like all the examples I'm going to talk about here are for what are called tri-tensors, which is the case d equals 3. But in some sense, this is one of those problems where d equals 2 is one level of difficulty, and then d higher than 2, you immediately jump to a much higher level of difficulty. And I don't know if 3 is that much easier than 4 or 5 or what have you, but it's easier to give examples about 3. So I'm going to focus on that case, but what I say should be thought of as for arbitrary large d. Okay, so a tri-tensor would be a sort of a rectangular parallelepiped, right? A sort of rectangular solid of numbers. Now, that being said, I do want to say this in a coordinate-free way. So let me say that a tensor, the reason it's called a tensor is because it's an element of the tensor product of d different vector spaces. So here, the dimension of vi is the number I called ni before. And if I endow each one of these with a basis, I can get back this rectangular array of numbers. Maybe worth saying, just so nobody complains, is that I'm sort of implicitly thinking of my vector spaces as all carrying a bilinear form. So in other words, when d equals 2, I seem to be saying a matrix is an element of v tensor v. It's slightly better to say a matrix is an element of v tensor v dual. That's what's canonically identified with HOM VV. So if we think of a matrix as a linear transformation, that's what we're doing. And I'll also say that, you know, if your matrix, if your vector space has a basis, you can identify it with its dual. And, you know, if we were really doing everything in a coordinate-free way, it might be better to keep track of like that distinction, but I'm not going to mostly do it today, if that's cool. Okay. So, so what is the rank of a tensor? How can we extend this notion that's been so useful into this higher regime? Which, by the way, you may say, why would I even care about this higher regime? I'm going to give some examples of applications so you can see that this is the useful thing to think about. So the problem is that there's no way to interpret a tensor like this as a linear transformation. Okay, that's not quite true, but it's certainly not a map from V to V. You can kind of think of it as like a bilinear map from V cross V to V. That's one way to do it. But that fails to capture a lot somehow. In some sense, I mean, this is not a direction I'm going to go in this talk, but in some sense, like plenty of the work on tensors does indeed take this view. And one way you can think of it, of what this is actually doing, would be, e.g., it's just like interpret your, let's say that the dimensions are all the same, your n by n by n box as an n by n squared matrix. You can certainly do that. Nobody stops you, and you'll learn something in the same way that, you know, the space of n by n matrices is an n squared dimensional vector space, and I'm perfectly free to write all the columns on top of each other and just think of it as Rn squared. And there's sometimes when that's a perfectly good thing to do, but you have to admit you're losing something about the structure of matrices if you do that. And in the same way, you're losing something about the structure of tensors if you take this point of view. So let me tell you what is typically done instead. So of the many, many, many equivalent definitions of rank, I'm going to pick out the very last one I said, because that seems to be the one that generalizes somewhat well. So we're going to start by saying, what does rank 1 mean? So in the case of matrices, rank 1, one way to say that is that it was matrices of the form V times W transpose. Okay. So here, it's actually, it turns out, unfortunately, there's sort of a bunch of different ways you can do this, and I'm going to tell you about 2 of them. The most analogous way is to say that a tensor is rank 1 if it is a pure tensor. That is, if it can be expressed as one vector, tensor, another, tensor, another. Okay, so maybe you like thinking about multilinear algebra and tensor products, and maybe you don't. So let me tell you what this looks like in terms of the box. Here's an example of a rank 1 tensor in this sense, right? So I'm going to do 2 by 2 by 2 because it gets really hard to draw these when they get bigger than that. So a 2 by 2 by 2 tri-tensor is a box of 8 numbers. The entry is a function of 3 variables, I, j, and k. And rank 1 in this sense, which is also called tensor rank 1, means that this function is some function of I times some function of j times some function of k. So in this case, I guess the 3 functions would be, here I ranges from just 1 to 2, so they're pretty simple functions, just 2 numbers. And here, I guess f1 would be just sending 1 to 1 and 2 to 2. F2 would be sending 1 to 1 and 2 to 3, and F3 would be sending 1 to 1 and 1 to 5. So I hope people can see that this cubey thing I've drawn, I think does have a right to be considered a 3-dimensional analog of, and I'm going to scroll back, my rank 1 matrix that I wrote down, like this thing, where it's, I mean, I just have to, I specify a function on the rows and a function on the columns, and then the entry is the product of those two numbers. Okay, let me find where we are. Yeah, that's one notion. Another notion called slice rank, and this is actually pretty recent. This was just invented by Terry Tao on his blog in 2016. I'll tell you in a little bit about the context in which that notion came up. If you can express it in one of 3 ways, either as a vector in one of the spaces, tensor something in the tensor, the other 2 spaces, or V2 tensor something in V1 tensor V3, or a little vector in V3 tensor something in V1 tensor V2. Okay, so again, if you like multilinear algebra, that's a very sensible thing to say. Let me say in terms of the cubes, it kind of means that you could take your function of 3 variables and factor out one variable function. So aijk, instead of making the more stringent requirement that it be a function of a times a function of j times a function of k, like complete decoupling, you say, well, I can pull out an f of I, and it's f of I times some unspecified function of j and k. So it's that, or it's the same thing with j playing the special role or k playing the special role. So here's an example of a little cube that is slice rank 1, because here, if you look at this top square, that's like a full rank matrix. 1, 3 has nothing to do with 2, 4, but everything on the bottom square is 5 times everything on the first square. So it's kind of like some arbitrary function of 2 variables times the function 1, 5. So that would be an example of slice rank 1. So, okay, we have at least 2 competing notions of what low rank means, or at least what rank 1 means. But now we imitate this fact we knew about matrix ranks, and we say a tensor has rank R, either in the tensor sense or the slice sense, if it can be written as the sum of R rank 1 things. So now we don't need any notion of like relation with linear transformation or like column space or like blah, 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 blah. This definition carries over perfectly well from the case of matrices. And these are the definitions that people usually use. So I'm going to remind you of this philosophy. I copied this from my previous slide, but now I want to kind of modify it a little bit. So let's say, instead of talking about rank, we're talking about tensor or slice rank. Now, it's still interesting, but it's very hard to compute. So because you lose the connection with linear maps, it turns out that it's actually not easy to compute these invariants at all. We can compute it for certain special cases, but I mean, like literally, if you have like a large tensor in your computer, it's not so easy to see what the rank is. Nonetheless, it's useful, and I want to give you two applications that I know about, which kind of mirror the two applications of rank I started with. And then if there's time at the end, I'll say a little bit about, because there's a lot more applications than these, and maybe I'll say a little bit more about them, including the most famous one. Okay, so application one is low rank, instead of low rank completion or approximation for matrices, low rank tensor completion and approximation. So I just put a Google Scholar search in it yesterday just to show you that there's like tons of papers about this. I got 195,000 results on Google Scholar for this. So this is definitely a thing that people do, lots of papers with lots of citations. So what's the philosophy? Okay, remember this philosophy? I copied it from the old thing. Now I'm just going to change it. So matrices instead of matrices, let's say tensors in the real world would like to be low. And maybe I'll say low tensor rank, because this notion of slice rank is pretty new. And we don't know yet whether it's like useful for data science. So usually the people in the data science community who think about this are talking about tensor rank. But the problems are very much the same. You have something that you measured, and you want, but there's some missing data. Either there's some missing data or there's some data that was measured imprecise. There's some missing data you want to fill in, or there's some data that was measured imprecisely that you want to denoise. You want to sort of find a better approximation to it. And the point is that in the real world, it's great if everything is like Netflix, where you're like, the number that you study is one user and one movie. But in real life, there are lots of things you want to study where there are more than two inputs. And then you're in this situation of having like a box of higher dimension of numbers. So basically, this is like saying the world is not all made of functions of two variables. Some functions are functions of more than two variables. So for example, here's what I learned about from my colleague Miaoyan Wang. If we study gene expression, traditionally, you have a bunch of people and you have a bunch of genes, and you sort of say, okay, I'm going to study like how strongly this gene is expressed in this person. But that can be like a little bit misleading, because it turns out that within the same individual, the gene can be expressed rather differently in different tissues. So I think a better way to sort of do this kind of analysis is you take the same person and you measure a bunch of different tissues from them, and then the level that the gene is expressed is actually a function of three variables: which gene it is, who the individual is, and what the tissue is. And if you measure all those things, maybe you don't measure every single entry or measure the entries imprecisely. You may want to approximate what you get by well, you get a tensor, and you may want to approximate it by a low rank tensor. Let me give one more example. I feel that one thing that's a little bit lacking. So maybe let me say one thing about why this problem is hard that I didn't put in the slides that I want to put in. So low rank matrix approximation, it really uses the so-called singular value decomposition. This is, if any of you folks are in data science or optimization, you know that this is kind of a workhorse method. Loosely speaking, I told you that low rank means that there are few non-zero eigenvalues. So what you do in practice with a matrix is you look at the singular values, and what you hope is that a lot of them are big and then some of them are small. Hopefully most of them are small. And then the ones that are small, you're like, well, those are probably really zero. I have a hypothesis that really this thing is low rank, and I measured it imprecisely, or maybe it's near something that's low rank. And so I can just take those singular values and I can force them to be zero by projecting onto their orthocomplement. So I just project away the part of the matrix that is supported by those singular values. And that just basically gives you the same, it's called a thresholding. You have the same matrix, the big singular values stay the same, but the small ones become 0. There's no theory of singular values for tensors as of yet. There's actually a lot of proposed theories of singular values, and all of them kind of capture some features of what's good about matrices, and some which don't, and some of them work better in some cases than some others. But there's not a quick and dirty SVD that you can just do. So I'll just comment that that's one of the things missing that makes it a hard problem to find a low-rank tensor near some tensor that you actually measure. Okay, so I can't resist talking about one of my favorite data sets, because it's a very clean data set. So you can get from the Social Security Administration any first name in any US state and any year from 1913 to the present. You can find out how many babies were given that name in that state in that year. I like this data set because it's very clean, like nothing's missing. It's like, it's all in a very nice uniform format from the US government. So you could just have this big tensor that's like, 50 by a little more than 100 by a lot, because there's a lot of different names that occur in this database, right? And then you can try to see if this is well approximated by a low rank tensor. Why would you want to do that if these numbers are precisely measured and they're complete? Well, one reason is, and just for reasons of time, I didn't go into this like so much in the first section of slides, is that approximating your matrix by low rank kind of has the feature of placing both your rows and your columns into a low dimensional space. That's kind of related to what we saw with these distance matrices, where embeddability into a low dimensional space was related to a matrix being low rank. So in the same way, if you take this thing and you make it into and you sort of have a low rank tensor that approximates, along the way, what that gives you is embedding of all the names to a low dimensional space, states into a low dimensional space, and all the years into a low dimensional space. Well, the years definitely belong in a low dimensional space, right? They belong in a one dimensional space. But I'll just show you quick, it's kind of cool what happens with these states and names. So here's the states, and what you're looking at here is, remember I told you that a low rank tensor, you can kind of express things in terms of like functions on the individual vector spaces. There will be like some function on states and some function on names. Here you see plots of the functions, and you see like very nice clustering phenomena. You see the one that carries the most weight is a function that's sort of strongly supported in the northeastern part of the US, but not New England, just kind of like New York, Philadelphia. They're sort of geographically concentrated. You have the second largest one is a function that sort of is strongly supported in the American South. And then you have sort of, I think we did this with about 6. Oh, and I should say, by the way, this is with, really the person who did the work here is Mujia Wang, who's a graduate student in statistics at Wisconsin, who's working on low rank tensor approximation, among other things. You can also, now it's a little harder to write down what a function on names looks like, but what we did here was, for each of the 10 functions we found, we wrote down the names that scored highest on that function. So you can see sort of which names they're giving a lot of weight. And I hope this is like not too small to be readable, but you can really see that this is actually picking out features of names that have something in common. So I would say this, oops, I meant to highlight, not write with red. These are kind of, I guess I would call them old-timey Anglo names, like Donald, Gerald, Harold, Raymond, Richard. These are, and Ronald. These are sort of names that have something to do with each other. Here, I would kind of say, like, roughly speaking, you have what I would call like the Catholic names. Like, these are probably strongly supported in the American Northeast, like Anthony, Christopher, Thomas. Here, you start to see with this one, you start to see the fact that time is a feature here, because these are all names like Austin. Well, here's Christopher again, ranks high in this one, but like Austin, Cody, Jacob, Ryan, Zachary. These are not names somebody was given in like 1950, probably. These are like more recent names. Here you see names that are like predominantly from the Spanish. So each, I mean, you sort of do this automatically, and it's clear that each of these functions that sort of falls out of the low tensor approximation is probably actually picking out something kind of legible about properties that the names actually have. So I talked about approximation as a means of doing, as a means of denoising leading data sets. It's also a means of visualization, clustering, et cetera, even if the data is perfect. Hey, so I think, Jane, I guess without even asking you, I sort of assumed I'm supposed to take an hour and go to 3:30. Is that correct? Or am I supposed to stop at 3:20, which it now is, or 4:20 for you guys, I guess? Am I cool?
Usually, I think 4:25 should be fine, or even a little beyond.
25.
Yeah, because
okay. So let me do.
Yeah.
Okay, so let me just say the last thing. So, and this is a thing I've given lots of talks about before. So, so here's another famous old problem in extremal combinatorics, the problem of cap sets. So the question is, and this is supposed to be parallel to the problem of S-distance sets I talked about before. But now it's taking place in a finite field instead of Euclidean space. I have a subset of F3 to the n, and we could do this over an arbitrary finite field, but I just want to make it simpler and just talk about one problem at a time, which has no 3 points that sum to 0. And the question is, how big can such a set be? And this simple problem is like actually really hard, and people, including me, worked on it for a long time with no success. Like, how big could this set be? And for a long time, basically the best upper bound was on order like 1 over n 3 to the n. And the best lower bound was like 2.2 to the n. Okay, those are like really different, right? So this is like one of these extremal combinatorics problem where we're like, what's the truth? And people truly didn't know. So I'll tell you how myself and Dion Gijswijk, following an idea of Krotlev and Potch, were able to get a much better upper bound that was an exponential, something smaller than 3. The idea is the following. You make a tensor, a tri-tensor, where, quite simply, you have some big subset of your space over F3, and you have a tensor. So this is just like we did with our endpoints in Euclidean distance. And now the tensor is just going to take values 1 and 0. Maybe I should say this is the tensor over F3. It's now over a finite field, but linear algebra works great over a finite field. And basically, it's 1 if the sum of the corresponding 3 points is the 0 vector, and 0 otherwise. So it's like a 1, 0 tensor. Now, in the interest of time, maybe I'll just like let you guys believe this. This is some facts about finite fields that you can also write the entry of this tensor as a polynomial in the coordinates of S1, Sj, and Sk. And in fact, it's a polynomial of degree 2n. So I'll just ask you to believe that as a fact about the arithmetic of finite fields, that you can make this polynomial, which takes only the values 1 and 0. But just like in the case of the S-distance set, the fact that I was able to, if I can express the entry of a matrix, or in this case a tensor, as some polynomial whose degree I can control, that actually allows me to control the rank. And it works for these kind of generalized higher ranks just as well as it works for regular matrix rank. So in this case, what you get is an upper bound, and it turns out here's where you need this notion of slice rank. So I should say now, I'll say the context, why was this notion invented later? Because Dion and I both were able to prove this theorem. We proved it independently and then wrote it up together, not really realizing, we expressed the proof in a different way, and then Terry read it and was like, oh, what you're really doing is using some notion of rank of a tensor, which hasn't been invented yet. So Terry sort of told us what it was really about, is really the notion of slice rank. We were giving an upper bound, and Krotlev and Potch too, by the way. So we were giving an upper bound for the slice rank of this tensor. But once again, just before, if S has this magical property that this is never the case unless Si equals Sj equals Sk, in which case, by the way, it's always true, right? Because we're in characteristic 3, so Si plus Si plus Si does equal 0. If S has this magical property, it's what's called a cap set, that no 3 elements sum to 0, then T actually is supported in the diagonal. And now here's a fact, which is not totally obvious, but I'm going to tell it to you. Just like with matrices, if you have a matrix, which is a diagonal matrix with non-zero entries, its rank is full. Same thing for slice. If you have a cube and all the entries are 0 off the diagonal, and the diagonal entries are all non-zero, in this case 1, then it has maximal slice rank, which is the size S. So conclusion, it has, so here it has, once again, we have a statement that this tensor has low rank and a statement that this tensor has high rank, which is a contradiction unless S is not too big. And that's the theorem of myself and Dion Chai's fight from 2016. So I guess I'd say the philosophy here in terms of geometric combinatorics is that if you want to bound something about large sets of points and the condition is on d tuples of points, you're going to need to use degree d tensors. So if you're content to sort of prove theorems about controlling distances, a distance is an invariant of a pair of points, so you can use matrices. But if you want to study three-term arithmetic progressions, which is really like what this is an example of, then you're studying relations between triples of things at a time, and you got to use ranks of tri-tensors. It's actually, again, for the combinatorists, it's kind of like the difference between studying graphs, which have to do with matrices, and studying hypergraphs, which is a lot harder, right? And that has to do much more with tri-tensors like this. So actually, I just thought of writing this down. I'm trying to see if any grad student to do this. For instance, a typical tri-tensor problem over the real numbers would be, suppose I have a big set such that if I look at every triangle, every 3 distinct points in this set, and look at all those areas, I get only k distinct values. How big can the set be? It's totally possible that like some Hungarian somewhere in the world has like solved this problem already, and I wasn't able to find the reference between when I thought of this on Wednesday and now. But this would be the kind of problem where these methods would be potentially useful. Okay, so we're just at the end of our time. I will comment that the most famous application, which I didn't even talk about, is rapid matrix multiplication and questions about the complexity of matrix multiplication. You can invite Joseph Ensberg about that. He gave a wonderful colloquia in Wisconsin about it. And I also won't talk about the relations between with commutative algebra, where you can relate this to questions about degree D polynomials and the commutative algebra notion of strength, which is also like really big right now in commutative algebra. I'll stop there with just those 2 applications on side. So thank you so much for coming. I really appreciate your being here.
Well, thank you, Jordan, for this wonderful talk. So let's see if there's any questions from the audience. Oh, please unmute.
I have a question. So this slice rank, when you have like n vector spaces that you're taking the tensor product, so rank n tensor, is the slice rank again defined like you only need to break off one of them? Or
yeah, that's a great question. So the higher the degree, the more things there are that you could do. So I would say the original definition of slice rank is exactly that. You can break off one. There is another notion that I think Eric Naslund wrote down called the partition rank, where it counts as rank 0 if you can express it as a function of some subset of the variables times some function of some other subset of the variables. But it doesn't have to be 1 and d minus 1.
Can I ask a follow-up question? I mean, so
yeah.
Like if the vector spaces say are just like CM, complex vector spaces, then we would think of the rank that you described for a tensor as like the rank 1 tensors would be like product states. We would think of that in quantum mechanics, and then these questions about slice rank in different partitions would be questions about multipartite entanglement and representing like multipartite entangled states using different representations. And one of the things that is popular would be to use like a tensor network. So how does that relate to these data science applications that you have in mind?
So it's a great question. Actually, I'm so happy that you asked that, because like literally, as I said, I'm teaching tensor products in graduate algebra, and like literally just this morning, I was like talking about how I just learned that like all entanglement is the fact that like not every element of the tensor product is like a pure tensor. And I was like, look, like it's okay. So, and then like I felt like none of my pure math students were like that interested in that fact, and I was like a little disgruntled. So thank you for asking and ratifying my claim that this is something that people who do physics actually care about. So this would be another, and actually I apologize because it's not in my mind right now, and if it were, but there is a paper, maybe you know the authors, it's completely fled my mind, I apologize, but where they do try to quantify the notion of how entangled a multi-particle system is in exactly this way. And so I should say that this definition kind of, I said Terry invented slice rank, but in some sense, like once you know what it is, you see things that are essentially equivalent to it a lot. So this notion of strength that I have on this slide, really you can see it in like old analytic number theory papers of Wolfgang Schmidt from like the 80s. And it's essentially equivalent. And I think this notions of like, that people are I've seen people, that mathematical physicists do, of like how entangled a point in a Hilbert space that tells you about the status of a multi-particle system. Please tell me if I'm saying something like wrong from the viewpoint of physics, because I'm very much not a mathematical physicist. But yes, like things like this. And actually, I think there's like a thing that I think is not very well understood, which I think the physicists probably understand better, is, you know, as mathematicians, we tend to say, oh, rank is like eigenvalues are non-zero and these eigenvalues are zero on the nose. Probably for a lot of situations, it's more relevant to have a softer notion where you want to say which eigenvalues are small in the rank case. You know, different matrix norms. We know a lot less about that for tensors, and it's possible that physicists know stuff that the pure mathematicians don't yet know, coming from exactly what you say. Like, but can I ask? I don't know who asked that, by the way. Who was that? Who asked the question?
Oh, that was David. That's me, David Gossett.
Oh, hi, David.
Hi.
So yeah, I'm curious if does this distinction come up for physicists between the difference between splitting off one particle from the other n minus one?
That's
versus...
why I asked. Yes, because you know, this question about generalization of SVD, it's a question of like, what is the right definition of multipartite entanglement? I mean, SVD is the same as bipartite entanglement, and we have a very rich theory of bipartite entanglement. It's completely understood how you can transform it, you know, how you quantify it, and so on. And the multipartite entanglement, there's many notions, and you know, it's exactly the situation you described. So yes.
Okay, awesome. So this is like a key word. I've seen some physics papers about it, but I don't think I knew this particular phrase. I'm going to write it down for myself, so I'll remember it, because I'm sure it's the same. It's the same genre of thing, and I would be interested to know. So who has good ideas about what a physicist would say is a good measure of this?
Yeah,
I could chime in and say that I think Matthias Christiandel has done a lot of work on this stuff. I think he's like kind of the, yeah, like I wouldn't be surprised.
How do you spell it? I'm taking notes on my own talk from your guys' question.
It's Matthias, Mattias, and Christandel is spelled Christandl.
Okay, I'm gonna remember that for myself.
He's got a conjecture that under stochastic local operators or local operations in classical communication, that essentially having 3 EPR pairs between the different like 3 parties is equivalent to having 2 GHZ states asymptotically, and that if that holds, then you can do matrix multiplication in quadratic plus epsilon time.
So that shows that obviously that person knows about the connection with like notions of tensor rank from pure math. If he knows about the connection to matrix multiplication.
Right, like there's this notion of SLOCC, which is really looking at like orbit under the general linear group acting on either of the 3 different like components of the tensor. And like you can view this as like doing like a quantum mechanical measurement that has to succeed with like one-sided probability, but it can be arbitrarily small.
Wait, is he talking about classical matrix multiplication, or is he talking about some kind of like quantum computer matrix multiplication? Classical, right? Okay, right.
Border rank basically is what it boils down to. It's like like geometric invariant theory kind of computation.
Yeah, and I didn't even get to talk about border rank in the sense that this tensor rank is badly behaved, and that the limit of something with a certain tensor rank, it can pop up. That doesn't happen for slice rank, actually. That's one way that slice rank is algebraically a little bit better. You don't have this border versus tensor. There's no border slice rank. It behaves well under limits.
Is that what you were going to mention in that direction? I was also going to ask, like, what was the other part that you didn't get to in your talk?
Well,
Great talk, by the way.
Well, maybe one thing I feel like for you reasons of time, I sort of said it, but I want to emphasize it, that somehow these ideas are present in a lot of different mathematical communities that are not really communicating each other that much. So just in this talk, I mentioned the people who do like additive number theory, like cap sets, the people who do extremal geometric combinatorics, like Erdős style geometric combinatorics, and data science. But then there's also the matrix multiplication people, right? So people in theoretical CS who do complexity of algorithms, and there's quantum mechanics people, and I didn't even say it, but I mentioned at the very end, the commutative algebra people who study strength of polynomials and many variables, and the number theory people who count numbers of solutions to Diophantine equations using the circle method, and that's Wolfgang Schmidt. And they have the same definition, which Schmidt calls the H invariant from the 80s, and sort of nobody recognized that this was the same thing as. So probably somebody's going to tell me tomorrow that like PDE people also care about this, or like mathematical logicians, or like who knows? I mean, it seems to be like it's a subject that doesn't have a name because there's like little pieces of it in a lot of different areas.
That's combinatorics.
It's combinatorics and optimization.
I had a quick question. So you mentioned that low rank is a small number of zero eigenvalues. Then later on, you also mentioned singular values. Is it more true that it's really the singular values that are involved with low rank, and eigenvalues really don't matter?
Well, okay, I would say speaking literally, low rank means many zero eigenvalues, and it really does mean eigenvalues. And the reason I would say that is because this notion, it's not just a real numbers thing, right? I mean, it's useful also over things like finite fields. That's where I first encountered it myself, where there's no notion of singular values if you're working over a finite field. That has something to do with the real numbers specifically. So I would say that if you are in a situation like with the S distance problem, where everything is naturally defined over R, then it can be very useful to do singular value decomposition for like effective computation. But I guess I would say, and I'm willing to be challenged on this, that what's really at issue is the eigenvalues of the linear transformation. I do think I would say that.
But all the eigenvalues can be zero, and you can have a high rank matrix.
So that is a great point. So I would say you're right. I spoke too cavalierly. So it's not literally the number of zero eigenvalues that's an issue, because you might not be diagonalizable. So that's an excellent point. I mean, I think of that as sort of a probability zero event, but it's something that you have to be careful about. Absolutely.
And the other, so just a follow up to that. So your distance matrix question, that's really, I don't know. I mean, some of us call that Euclidean distance matrix. I guess, I don't know if you do as well. So there's a whole, right, EDMs. So the idea of having low rank there essentially means all your points are actually lying in a low dimensional space, right?
Exactly.
Exactly.
And like,
so low rank and low dimensional space is essentially just one rank off, one dimension off.
Right, absolutely. And it's something that people, people who do like, again, the data science people who do embeddings, they will constantly be sort of like measuring distances and trying to hope that they get a low rank matrices, or, they believe that they sort of believe that real life things tend to like live on a low dimensional manifold. That's sort of part of the low rank philosophy.
I have a question. Do you believe the base of your exponent for cap sets is correct or close to correct?
That is a very vexed question. I don't think anybody really has like a good idea about whether to expect that or not. I can tell you that there are variants of the cap set problem where instead of having the same set and looking for solutions in S satisfying this, you can say I have S1 and S2 and S3, so 3 different sets, and I'm matching between them, and then you ask that there be no solution little s1 plus little s2 plus little s3 equals 0 apart from the matching. So it's something we call the multicolored cap set problem. So it's a slightly more flexible problem, and for that, this method actually applies to that problem just as well. giving the same upper bound, but there it's known to be sharp. So it's I hope I can remember everyone. Kleinberg at Cornell, and I think David Spire, and oh my gosh, I apologize because there's multiple authors here and I'm not remembering them all, but like it has been shown that for a more flexible version of the problem, that bound is actually sharp, but nobody knows for the original capset problem. And in fact, this lower bound has not really been improved for like decades.
Well, I think it's probably time to stop the colloquium, and I think if Jordan is going to hang around a little bit, we can have more discussions. So
Awesome. Well, thank you guys so much.
Jordan again for the wonderful talk.